let us see what is meant by transformer and what are the basic concepts that we are going to discuss here. First one is, in this transformer we will concentrate on principle of operation, where we have already seen in the basics of our electromagnetism, and the second one is about ideal transformer, okay, at no load and full load condition. Next one, a practical transformer, all right, and then equivalent circuit, phasor diagrams, all right. Next one, different types of losses available in the transformer and how to reduce them. Once you calculate the losses, then how to calculate the efficiency of the transformer, then voltage regulation, fine. Next one is auto transformer, and finally we will discuss about three-phase transformers. All right, so these are the concepts that we are going to discuss in this particular module. All right, now let us see first the principle of operation of this particular transformer. We have already seen in the basics of electromagnetism, the principle of operation for a transformer is Faraday's second law of electromagnetic induction. Okay, so according to Faraday's second law of electromagnetic induction, what happens whenever a conductor is placed inside a variable magnetic field with respect to time, obviously EMF will induce across the conductor. All right, so first of all, before moving to this principle of operation, let us see what are the various characteristics of a single phase transformer. All right, now coming to the characteristics of a single phase transformer, important characteristics I would like to write here and you also note down. So first characteristic is, transformer is a constant frequency operating device. This is very important. Constant frequency operating device. Next one, constant power operating device. Constant power. But you can change voltage. Voltage can be changed from primary circuit to secondary circuit. Similarly, current can also be changed. Current can also be changed from primary circuit to secondary circuit. All right, so these are the basic characteristics of a transformer, and we will see how it will be operated and what are the important parameters and various things that we will observe. All right, so once you note down these, constant frequency operating device, constant power operating device, but voltage can be changed from one side to another side and current can also be changed. Okay, so next thing, basically a transformer will consist of more than one winding on its magnetic core. More than one means it can have 2 windings, 3 windings, 4 windings, any number of windings, but at least more than one. That means at least 2 windings will be there. Okay, now we will see how the transformer will be operated and what is the principle of operation, that is Faraday's second law that we discussed. And for this principle of operation, first I would like to consider an ideal transformer. I will consider ideal transformer. So what are the ideal conditions there when the transformer will become ideal? Okay, what are the conditions that must be satisfied to assume a transformer as an ideal one? The first condition that must be satisfied for the transformer to be assumed as an ideal one is, we will assume the winding of the transformer does not have any resistance. There is no resistance for the winding what you are considering. All right, now second condition that must be, actually every winding will have finite resistance, but if you assume the resistance is equal to 0, that will become an ideal condition, that is not a practical condition. Okay, next one is leakage flux. Leakage flux is 0. No leakage flux is available in an ideal transformer. All right, and the third condition that must be satisfied are core losses are equal to 0. are equal to 0. That we will discuss later. What is mean by core loss and all, what are the characteristics that we will see in the subsequent lectures. Alright. So, an ideal transformer does not have any resistance, does not have any leakage flux, and does not have any core losses. Okay. Such kind of a transformer we will call it as an ideal transformer. But practically these will not exist. First we will see ideal conditions, then later we will move to practical conditions. Alright. Now, I said already a transformer means it is a static device, because according to the principle Faraday's second law, transformer does not have any moving parts, it is completely a static device, and it will have at least more than one winding. Okay. So, for that purpose what I am doing is I am considering a simple magnetic core. I am considering a simple magnetic core. Assume this is the magnetic core that we have, and on this magnetic core we are wounding some wire with finite number of turns. Assume number of turns are n1 on this winding, and assume there is one more winding, because I told you transformer is a device which will have at least more than one winding. Assume there are n2 number of turns on other side of the transformer, n1 number on one side, n2 number on other side. Alright. Now, we will give some supply voltage to this transformer. Assume this is V1, which is given as the supply voltage, and I am assuming the transformer is under no load condition. That means we are open circuiting the secondary side, there is no load connected here. Alright. Now, one thing is that when a supply voltage is given which is of alternating in nature, obviously an alternating current will be produced, and I will assume the current as I naught here. I naught means the current flowing through the transformer winding when there is no load connected. Okay, that means indirectly I naught I can call it as no load current. No load current. Obviously. Okay. So, this is the current I naught. So, whenever current is passing, what will happen? Because finite number of turns are there, current is also passing. So, obviously a magnetic field will be produced in this direction. Okay. So, assume this is the direction of the magnetic field which is produced by this no load current. Okay. Or simply we will call this no load current as also as magnetizing current. Why? Because the current was drawn only for the purpose of creating the magnetic flux. That is why this current is known as magnetizing current. Okay. Now, whatever the flux is produced, we know flux is always a closed path. It will flow in this direction, and finally it will cut all the secondary number of turns also, and it is cutting the primary number of the turns also. Okay. Now, one more important thing, this is an alternating voltage. So, obviously current is alternating in nature. If current is alternating, what is the flux that can be produced? Is alternating. Why? Because what is the relation between flux and current? We know flux is equal to mmf by reluctance. We discussed already. Mmf is nothing but n into I by reluctance. So, flux is proportional to the current whichever is flowing. So, an alternating current is flowing. So, obviously an alternating flux will be created. Okay. Now, when this alternating flux is moving through this magnetic core, look at here, this alternating flux is now interlinking or linking all the number of turns available on the core. Alright. How many number of turns are there? N1 number of turns are there. So, it is linking all the number of turns. So, obviously what will happen? An EMF will be induced on the first winding of your transformer. This induced EMF we will call it as primary induced EMF, E1. Why? Because this first winding to which the supply voltage is connected is known as primary winding. Okay. And the rest of the windings we will call it as secondary winding. Alright. So, now an EMF will be induced on the primary winding. Why? Because flux is interlinked. In how many turns the EMF is induced? N1 number of turns. How much flux is flowing? d phi by dt. This is the value of the EMF induced in the primary winding of your transformer. Okay. Now, one more thing, the same flux which is created by the primary winding is also flowing, and it is linking the secondary number of turns also. Yes or not? because the flux is always a closed path, it is passing through the magnetic core. So when it is passing through the magnetic core, it will link the secondary number of turns also. How many number of turns are there in the secondary winding? N2 number of turns are there. So therefore an EMF will be induced in the secondary winding also, we will call it as E2. The EMF was induced in the secondary winding, we will call it as E2. So now tell me, what is the formula for E2 according to Faraday's law? E2 will be equal to, how many number of turns are there? N2 number of turns are there. And what is the flux flowing? Phi is the flux flowing, so it is N2 into d phi by dt. Alright. Now if you consider these two equations and let us take the ratio between these two equations. Therefore the ratio between E1 to E2 will be equal to same flux, it is same flux, therefore d phi by dt and d phi by dt will be cancelled, so which is equal to N1 by N2. This is the ratio of the transformer voltages, or simply we will call it as transformer voltage ratio or transformer turns ratio, which is very important. Got it? So transformer voltage ratio or transformer turns ratio. Therefore primary induced EMF with respect to secondary induced EMF is equal to primary number of turns. N1 is primary number of turns with respect to secondary number of turns. Alright, fine. So now what is the type of supply we gave? We gave alternating supply, so alternating current will flow. So whenever alternating current is flowing, alternating flux will be produced. So I am assuming flux is equal to phi m sin omega t plus 0 degrees. That means it is taken as the reference 0 degrees. Alright, this is the flux which is flowing. Why? Because it was produced from a sinusoidal current. Alright, fine. So now if phi is equal to phi m sin omega t plus 0, then what is d phi by dt value? D phi by dt is nothing but now d by dt of phi m sin omega t plus 0 degrees means sin omega t. Phi m is the maximum value of the flux, so I can take it as out of the derivative. So it will become phi m into derivative of sin omega t means it will become omega into cos omega t. Got it or not? Sin omega t derivation is cos omega t simply. Okay, this is a d phi by dt value. Okay, now let me replace this d phi by dt value in these equations. We have seen already E1 is equal to N1 into d phi by dt. So therefore E1 is equal to N1 into, in place of d phi by dt, what we can substitute? Phi m into omega into cos omega t. Alright or not? And now what is the polarity of induced EMF? When I said EMF, obviously it must have a polarity, positive polarity and negative polarity. So how to identify the polarity of induced EMF? Very important, polarity of induced EMF. Okay, so write that polarity of induced EMF. This is statically induced EMF or dynamically induced EMF? This is statically induced EMF. Why? Because conductors are stationary, magnetic field is variable with respect to time. So therefore the polarity of induced EMF can be identified using Lynch law. We will use Lynch law to indicate the polarity of induced EMF. Very important principle, Lynch law. Okay, so let us see what is mean by Lynch law. The statement of Lynch law is, according to Lynch law, the effect will always oppose the cause of production. The effect will always oppose the cause of production. Alright, this is what Lynch law is stating, that the effect will always oppose the cause of production. Now let us see what is the effect here and what is the cause. The effect is nothing but the induced EMF over here. Okay, induced EMF is the effect over here. And what is the cause for the production of this induced EMF? The cause for the production of induced EMF is the changes in flux linkages, d phi by dt. Okay, and what is the cause for the production of d phi by dt? First of all, if phi is there, then only d phi by dt will be created. So therefore phi is the reason. What is the reason for the phi? Magnetizing current Im. And what is the reason for magnetizing current? Is nothing but the supply voltage. So indirectly the reason for this induced EMF is nothing but the supply voltage. Okay, so here effect is the induced EMF and the reason for this induced EMF is nothing but the supply voltage which is given by V1. Okay, therefore what will happen according to Lynch law? This is the effect that we have, and this is the cause for the production. Now according to Lynch law, there must be an opposition between the two, or support between the two. Opposition. Why? Because it is stating that the effect will always oppose the cause of production. Okay, there will be an opposition between the two. These two will oppose. That means, what is the meaning of it? If these two are opposing, means indirectly, if I assume the supply as positive, then obviously induced EMF will become negative. Am I right or not? Why? Because this is the cause, this is the effect, both are opposition, and according to Lynch law, both will oppose. So therefore, if you assume the supply voltage as positive, obviously induced EMF will become negative. Am I right? Okay, fine. So now, to indicate that Lynch law, what we are going to do is, we will provide a small negative sign over here. What is the meaning of that negative sign? The meaning of that negative sign is, induced EMF is opposing the supply voltage. Indirectly, if I take the supply voltage in this phase, let us assume supply voltage phasor is given like this. This is the supply voltage. Then what about the induced EMF? Induced EMF will obviously oppose the supply voltage. Is it the meaning or not? Why? Because according to Lynch law, both must oppose each other. Got it? Okay. If you assume this is a positive, obviously this will become negative, to indicate that there was a negative sign provided. All right, fine. Now once the negative sign is provided, let us further move with our induced EMF. So E1 is equal to this minus sign I am representing here, N1 into phi m into omega into minus cos omega t. All right, minus sign I am writing here. Cos omega t means I can also write cos omega t as minus of sin 90 minus omega t. This is what we know. Cos omega t can be written as sin 90 minus omega t. Now let us multiply this minus over there. Therefore 180 degrees phase reversal. That means it will become omega t minus 90 degrees. Got it? So indirectly, induced EMF is equal to N1 into phi m into omega sin omega t minus 90 degrees. All right, fine. So therefore, look at this. The flux we considered initially is phi m sin omega t plus 0 degrees. This is at 0 degrees, and the EMF whichever is induced is N1 into phi m into omega sin omega t minus 90 degrees. So from this particular point, you can understand that the flux is at 0 degrees, but the induced EMF is minus 90 degrees phase. That means induced EMF is lagging the flux or leading the flux. It is obviously lagging the flux. Okay. So therefore, if I assume flux is my reference, assume the flux is my reference waveform. Okay. So that means it is at 0 degrees. All right. Then what will be the induced EMF? Obviously, induced EMF is lagging the flux by 90 degrees. So this is the value of induced EMF. It is lagging. Lagging means clockwise direction. All right. And leading means anti-clockwise direction. All right. So this is the induced EMF lagging. This is E1. Now, according to the Lynch law that we discussed, obviously induced EMF is always opposing the supply voltage or supporting the supply voltage, opposing the supply voltage. That means induced EMF is in this phase, means obviously supply voltage will be exactly opposite to your induced EMF. Got it or not? And one more thing is that, where is the current that is drawn by the transformer? That is magnetizing current. We have seen what is the purpose of magnetizing current. The purpose of magnetizing current is to create the flux. So therefore, the current, magnetizing current, will be in phase with flux. Why? Because we have concluded flux is always proportional to the current. Therefore, current, magnetizing current and flux both are in phase with each other. This is nothing but the current which is drawn by the transformer from the supply. Okay. So if you look at this particular phasor diagram, this is the supply voltage V1 and this is the induced EMF E1, and this is the flux under, that is nothing but also the current drawn by the transformer. So therefore, what is the power factor at which your ideal transformer under no load is working? Okay, this is ideal transformer under no load condition. So look at this. This is the supply voltage, because we know power factor angle is nothing but the angle available between supply voltage and supply current. This is the supply voltage, and is it nothing but the phase of supply current? So obviously, what is the angle available between the two? 90 degrees, and current is lagging the voltage or leading the voltage here? the current, magnetizing current is lagging the voltage by 90 degrees. So what is the meaning that the current is lagging the voltage by 90 degrees? That means indirectly it is power factor lagging 90 degrees angle, means obviously it is going to be cos 90, that means 0 power factor lagging. Got it? 0 power factor lagging means indirectly it is a poor power factor or a fine power factor, very, very poor power factor. That is why a transformer under no load condition will operate at very, very poor power factors. You should not operate transformer under no load condition. So this is the phasor diagram of the ideal transformer under no load condition. And this is the induced EMF equation that we got. E1 is equal to N1 into phi m into omega sin omega t minus 90 degrees. Okay, let us consider now induced EMF equation once again. Induced EMF is equal to N1 into phi m into omega sin omega t minus 90 degrees. From this particular induced EMF, you can identify it is looking like a voltage is equal to Vm sin omega t minus 90. So that means this is representing the maximum value of this voltage, and it is obviously a sinusoidal voltage. Alright. So if this is the maximum value of the voltage, then what will be the RMS value? If the maximum value is this much, then what is the RMS value of a sinusoidal waveform? We know. Once you know the peak value, you can easily calculate the RMS value, which is equal to N1 into phi m into omega by root 2. This is the formula for RMS value. Am I right? Okay. Now let me rewrite this one. N1 into phi m into omega means I can write 2 pi f by root 2. If you solve this one, the RMS value of the induced EMF is equal to 4.44 phi m f into N1. This is going to be the equation that you are going to obtain. Now this is the induced EMF on the primary winding of the transformer or secondary winding of the transformer. This is the induced EMF on the primary winding of the transformer. If you apply the same principle on the secondary winding of the transformer, then you will get E2 RMS value will be equal to 4.44 phi m f into N2. This time you will get, because secondary winding will have N2 number of turns, which is N2. Got it? So now let us see what 4.44 is constant, phi m is nothing but the maximum value of the flux, f is nothing but the frequency at which your transformer is operating, N1 is nothing but primary number of turns, N2 is nothing but secondary number of turns. Alright. Now if you take the ratio between these two, E1 RMS value to E2 RMS value, so 4.44 phi m f everything will be cancelled and only N1 by N2 is the remaining one. So this is the principle we proved already. Okay. So every time I will not write RMS, I will write simply E1 and E2. So by default E1 and E2 are representing peak values or average values or RMS values. They are always representing the RMS values, N1 by N2. Got it? This is the value of induced EMF in a transformer.